Next talk is Projective presentations of Flex Modalities by Mark Williams.
Okay, so today I'm actually maybe continuing a talk. I didn't realize this was going to happen, but I'm continuing a talk from yesterday, maybe, if you think hard enough, which is that yesterday Jonas described this two-step process for checking a topos, sort of a synthetic theory for the topos. And his step was this generating this pre-sheaf topos. And my step is now doing part two, doing the sheafification. So, okay, I'm come today as a sheaf salesman. Okay, normally the adage of synthetic mathematics is that we work inside, we never have to see sheaves. But externally, sheaf theoretic methods is super useful, right? To do synthetic mathematics, a lot of it, we create topos of sheaves, and then we check a bunch of internal language properties using sheaf theoretic methods. Okay, but sometimes we need sheaves internally as well. Okay, so sometimes I'm working inside a topos, but I don't actually want to live in this topos anymore. I mean, in synthetic algebraic geometry, we've actually just seen an example. We were working in one topos, and we needed to construct this select modality for this Ital simplification, which is this one in the middle here. And further, there's more, there's like a billion that people consider in actual algebraic geometry, but maybe I've just listed 3 here. Or maybe there's triangulated type theory. They start with a larger universe, they need to construct some Lex modality. It's the same thing as doing a sheaf topos internally. Okay, and so I'm going to argue that maybe the nicest way to work with these internally, at least systematically, is just by using sheaf methods inside as well as outside, because we can just work with the theory of abstract Lex modalities, but you're going to get stuck maybe. It's not going to be obvious what to do. Okay, so let's recall what sort of sheaf look like inside. So given a family of propositions, type is a sheaf for that topology. It's the sort of internalization of a topology if it believes all of those propositions are true. So that means that a point of X is, to specify a point of X, it's enough to do it assuming the proposition, one of the propositions is true. Okay, and with this, we get a sheafification functor for free by higher inductive types. And these sorts of things, a choice of a sub-universe, sheafification functor. So with this data, a family of propositions is a topological modality. This is the thing that externally corresponds to a Grothendieck topos. Okay, so now I'm going to define a slightly more general notion, and it's not a lot of stuff, and I mean, actually, Ugo defined this notion, I'm just stealing it. But the point is that we would like to have a more sheaf theoretic notion of generators for our modalities, okay? And for this, it's very simple when you try and figure out what this should be. You should just take any collection of types, pretty much, okay? It doesn't really matter what you choose. As long as it's closed under sigma and it contains 1, but you can force any collection of types to do this very easily. Okay, and given a presentation, it presents the modality asking that all of those types be inhabited. Okay, so if you're familiar with the external perspective, you should maybe think of these as being covers of 1, and we're asking that covers of 1 are actually surjective in the subuniverse. Okay, there's some very simple examples. So obviously, as a trivial example, just take t equals 1. And actually, given any topological modality, there's an obvious presentation. And because it's propositions already, proposition truncation does very little. Okay. More interesting examples need new axioms, because we're doing synthetic maths, we want to come up with topologies, and if you're working in set, there's no good topologies, right? Okay, so the first example we've kind of seen already in synthetic algebraic geometry. The synthetic algebraic geometry as a ring and some of the axioms that Ugo described. And we can take a bunch of natural examples of these presentations. So last talk, we saw a slightly different one, but this is the collection of 0 sets of monic polynomials. So this asking that all of these are inhabited is the same thing as asking that the ring is algebraically closed or something. Every polynomial has roots. Okay. In simplicial and triangulated type theory, well, this adds a distributive lattice, and we ask that the topology, the presentation that we should give, should ask that the interval, this lattice, is actually ordered, totally ordered. Okay, and notice that both of these things are naturally presented not as propositions, but as asking that certain types are inhabited. And that's a common feature. If you look at a Grothendieck topology, it asks that certain things are inhabited. It doesn't really care about just asking that propositions are true. Okay, to show the use of this sort of method, we're going to do two things, okay? And the first thing is we're going to try and come up with an internal way to determine which types of sheaves. So we have this general condition, but it might be very hard to check, okay? And actually, we kind of know how to check certain types are sheaves externally, okay? The answer is just use sheaf conditions because they're sheaves. And sheaf conditions are really easy to work with in general. Well, okay, we can't really just use a single sheaf condition in hot because that would correspond to, the normal one corresponds to sheaves of sets, but you have big sheaves in hot that don't correspond to this. So really we need some higher. So for each n, we'd like a condition for an n type to be a sheaf that is like the sheaf condition. Okay, so to prove this, we're going to have to extend our notion of, so we had these types in our presentation that were covers of one. We can very, very easily generalize to covers for any pair, and that's just whose fibers are NT. So the fibers we want to be inhabited. Same thing as asking it's surjective. So it's these maps become surjective in the solid universe. Okay, and because of what I asked about topologies, these are, any equivalence is a cover, and they're closed on the pullback and composition, like covers you'd expect. Okay, to define sheaf conditions in the higher sense, it's hot. We're doing n groupoids. We're going to want some kind of homotopy construction, and the solution to this is going to be joins. Okay, and joins are going to encode enough of this. Well, we'll see the shape of the sheaf condition come out of joins in a second. But maybe we've seen this construction before, but you can take a join like this, and then given a single map, we can just iterate taking the join over and over again. And the point is that as n increases, this is going to look more and more like the propositional truncation, or the image in this case. It'll look more and more like the image of it. Okay. And it's going to turn out that the image of the map is going to control whether it's surjective, obviously. And if you're going into an n type, then the n+2 join is enough to control the whole image. So you don't need anything. So here you go. If X is an n type, then X is sheaf. If and only if for all covers, this map is an equivalence. Okay, so this is kind of easy, like not particularly hot, just machinery to get this result. And once you have this, you can kind of do sheaf theory. But okay, I may be lying, so this does not look like a sheaf condition, but it is. Okay, so here, why is this a sheaf condition? Well, I'm going to exercise the case in n = 0 for the usual sheaf condition. Well, there we can expand things out because joins are given by co-limits, and then we're exponentiating so we can get a limit at the end of it. And a zero type set is a sheaf if and only if for all covers, this map is an equivalence. And if you, in your head, shift all of these, instead of being exponentials, to be applications of a sheaf at a value, this is the usual sheaf condition. So now we have already recovered a sheaf condition. And if you have enough time and enough coherence conditions, you can generalize this to 3 or 4, but not any n, because that would be solving a problem I don't know how to do. Okay. So why is this actually useful? Well, okay, the idea is that using these conditions, we can just reduce most questions about whether something is a sheaf to just pure algebra, okay? So if, for instance, what we can do is we can apply this sheaf condition to get some limit of exponentials, and then using the axioms that are true internally, we can just reduce to a question of pure algebra. So like a one-step reduction from the sheaf condition says that the type I, which is a set, is a sheaf, if and only if this is an equivalence, and this is just algebra. Same thing for checking that the ring is a sheaf for the other topology I put up, the FPPF one. It's just all reduced to pure algebra. And this is easy to check, mostly because we know how to do it outside. It's just algebra. It's the same inside and outside. Okay, let's go on to round 2 then. So that's one case of how this is useful. Let's now try and do something else. Okay, so externally, if we're working in a pre-sheaf topos and we're sheafifying, pre-sheaves are projective, and this is like an easy category exercise, and it's nice. In fact, they're all tiny. Okay. Well, internally, this can be seen, so that's nice. So type X is projective if it satisfies the axiom of choice families over it. Okay, we'll call presentation projective if every element is projective. And the idea is that you want your presentation to be made up of representables, so they should all be projective. Okay, modulars of side vectors. Okay, both of the running examples are projective, at least in models. Okay, the one in SAG really is, that's part of the axioms. Triangulated type theory doesn't have this axiom, but it's true in their intended models, so they could do this. Okay. So what's the point? Well, the point is that projectivity is a condition on these types, and actually it's going to descend to the sheaf universe, and this is going to be a very, very useful property. So if we have a projective presentation and a projective type, then given a T locally merely inhabited family, then, well, we can't exactly find just a full section, but we can find a cover on which there is a section. This is kind of the trick that goes on locally. Okay, so this is very easy to prove as well. And the use of this is that now we can do some very general facts about cohomology. It's going to be the second use. Okay, so given a type X, we classically, like in hot stuff, we define the cohomology like this. And given a presentation, it's very, very easy to check that the Eilenberg-MacLane space in the sub-universe is just given by sheafifying the external one. And set truncation is given by sheafifying set truncation. So for any projected type, we can, and also we're going to generalize this result. So given any, or specialize this. So for any projective type X, its cohomology is 0. This is easy as well. And you should think of maybe cohomology as actually detecting how close to having choice something is. So in the sub-universe, we want to know, how does cohomology descend for projective presentations? Well, why should we expect there should be some descent here? Well, it's because we have local covers. I've already proven a kind of choice principle. Okay, so internally, we can now just define the cohomology in the sub-universe just by applying sheafification everywhere we need to. And we could now write down a very, very easy condition to check whether the cohomology descends. So this is just a simple, okay, so here's the condition that we need. So given the Abelian group A and type X, we can cook up an exact sequence, or a sequence like this. And it's just given by pairwise differences. So given any X, given any A, we can define a function which takes the pairwise differences. Okay, the same thing, but we're going to drop one element and do pairwise differences here. Okay. And given such a presentation, given a presentation and an A, say it satisfies descent, which is a magic word, it doesn't mean that much for T, if for all X, this sequence is exact. Okay, this is kind of a technical condition, but it's maybe motivated by outside. And given this, we're done, because this tells us that sheafification, or that the cohomology in the sub-universe now is the same as what it was outside. It's 0 for projections outside, and now inside, it's still 0. Okay, which is not obviously true in general, but here's the proof sketch. Take any cohomology class, and sort of by definition of the Eilenberg-MacLane spaces, this is always going to be a constant map, okay, merely pointwise. Okay. But actually, we have this local choice, so we have a cover of X for which this map really is constant. Okay, not on the type X itself, but on some cover. Okay, this doesn't actually show that this pi is constant, but I wrote the descent condition so that it gives you this. Okay, so descent for A is precisely what lets you convert any local constant function to an actual constant function, and that's it. Okay, and as a corollary of this, we can now prove something new in synthetic algebra. So it's very, very easy to check. So this is for algebraic geometry and thesis, so don't worry if you don't care. But in synthetic algebraic geometry, we have a very nice class of modules that satisfy descent. It's like I picked the condition. Okay, and this result directly applies. And so including the ring R, these all have 0 cohomology. And then there's some lovely work of David Vaughan and Thierry and Felix on check cohomology, which allows you to extend this upwards. So because quasi-coherent sheaves are nice enough. So actually, these have 0 cohomology everywhere. Okay, and this was all sheaf theory. So that's all I want to say right now, but just as a little conclusion, I think that sometimes when I stare at modalities, I get very, very stuck looking at all this general machinery. Sometimes I just want to write down a computation. And actually, the nicest way to write down computations is also the nicest way to write down computations internally. Just use sheaf conditions. Okay, thanks.
I think we actually have a lot of time for questions. So, any questions?
So in infinity toposes, you also have cotopological modalities. Have you given any thought to sheafification with those?
Yeah, I did give some thought to this, but I reckon that it's probably quite hard in HUT because if you want to describe a sheaf condition for a cotopological modality, you probably need to solve the coherence problem because they're given by some hyperdescent condition, and this is normally a very big. It requires a diagram with lots of coherence, and you can't write it down. So probably it's hard.
Right. Have you thought about sheaf conditions related to like CD structures and the sense of Voivodski? If you're familiar with these at all?
I've never heard of it. I don't know.
Okay.
Sorry.
Yeah, I mean, so maybe more generally, we looked at my other examples outside algebraic geometry.
Yeah, well, so we have this example from simplicial type theory. So this is but then so actually so when I do these two examples at the beginning, I can get all the way back. These two examples are essentially the same example. So given any algebraic theory, you can add the same axioms to your type theory as in synthetic algebraic geometry, and it's valid in a model, in models. So given any algebraic theory, you can do these sort of axioms. And then if you want to construct, so that you're working in the classifying topos of that algebraic theory, if you want to now take some quotient, some sub-theory of this, then you just need to find electromodalities. So that's the general setting that I've worked in.
So you have these two different definitions of sheaves. One was for a family of propositions, and the other one was to make certain types inhabited.
Yes.
And then you said to translate, you take P equals like one, like union of one plus P or something like that. Can you say that again?
Yeah. So the point is that there's the point is that if you think about it, given a family of propositions, if you treat that as a presentation, right, asking that all of the propositions are inhabited is the same thing that asking that all the propositions are true. That's just being a proposition. But in order to enforce it being an actual presentation, it needs to be closed under sigma and contain while. So I close it under sigma and add one. And it presents the same thing. So it's really just, there's very little.
So you're probably aware that there's some related work in higher topos theory by Dimitri and Biederman and Royale, I think.
Yes. Yeah.
So I can see more about the connections.
Yeah, that would be good. I mean, they consider slightly different notions of Grothendieck topology than I consider, with different closure conditions, but not all of their properties internalize so well, because oftentimes they're things that are only viewed outside. But there's probably some other sorts of classes that you can take that appear naturally in other settings. It's just for the case of like Grothendieck topologies, you're always thinking about covering. So that's why we do covering here. But maybe they have other sort of notions, monomorphism topologies, other things. They've got loads of versions. They've like
Yeah.
5 or 6. So.
Questions? Yeah, well, actually, I guess like it's not really a question, but it's like a remark for me. So this is actually I think it's a nice result to me. This is actually examples from the feasibility period as well. So you can apply some of these in realizability models, which is nice.
Maybe, yeah, but reliability models are not traditionally sheaf models, right? So
Yeah.
but they maybe have enough projectives for these results to work, or you can take internal.
Yeah, I mean, this is very well. We can discuss it later. I think.
Okay.
Okay, no more questions. Okay, thanks again.